Okay, let's go back to the where we were. So the agenda. So introduction to RISC-V, then something about vector computing that looks like different, but in the end we are going to put it together because I'm working on building a system that is based on RISC-V and has a vector unit. If you don't know what it is, you are going to learn it hopefully this morning. So RISC-V, vector computing, we put it together. I can explain you what's the project in which we are working now, and we hope, and that is relevant to HPC right now. Then we need tools to measure performance. So RISC-V, vector plus tools. And with these three components, I can show you a couple of examples of the kind of study that we can do. Okay, so that's the agenda for the morning. Maybe this can be in another, forgive me, but BSc. So the logo of BSc, you can see it here. So you don't need it. Good. Okay, let's start, as I said, from the Barcelona Supercomputing Center, where I come from. So from big to small, so top to bottom. Okay, so BSc is a huge data research center, data center in Spain, based in Barcelona. We operate the supercomputer. Do we have the pointer? Do you see the pointer? Yes. Okay. We operate Mare Nostrum. It was famous because it was installed in a church. Have you been visiting? How many have been visiting? Yeah. So I talk in the past because now, so since 1 month and something, we are now operating Mare Nostrum 5. That is a standard supercomputer installed in a basement. So it's boring. Well, it's nice, but it's more common. It's not installed in a church, right? So supercomputer. Then we have research and development. And then we are also connected with the university, so we can graduate students. We have PhD, and we have public engagement. So we have these three souls all together. Who pays for this? The Spanish government, the local regional government, and the university. Okay, so this is just for you to know big things. BSc. Now, one thing that is important in BSc, as I said, we operate a supercomputing. We are in an HPC summer school, so let me just spend one slide saying the story of Mare Nostrum. So the nice thing are the green boxes. Okay, so we started with Mare Nostrum 1 in 2004, I think. I don't remember. Okay, and the power in flops. Flops is a unit that is very useful for today. Do you understand flop? If not, stop me. Floating point operation per second. Okay, good, very good. So it was 42.3. It's not important, but it's one box. Okay, so then we got an update. And we got 2 boxes. Okay, so every 5-6 years we got an update. Okay, and that's the last update. Okay, so you can imagine basically in 20 years. Well, you can visualize, not imagine. You can also compute, which is the factor of improvement. Now I start doing the first arithmetic in public. You know that you don't do arithmetic in public because you always screw it. So from 42 to 204 petaflops, here I jumped of a factor of 1,000 and a factor of 5, right? So that's basically what you see in the green boxes. That's impressive, okay? So how do we get this kind of evolution? There is a lot of technology behind. I know that there are a lot of NVIDIA people in the room. There are, at some point, the GPUs appeared here, and they pushed a lot the flops and so on. But okay, so that's just for you to give you the idea. Right now we have 4 partitions. GPP is general purpose processor, or standard CPU, Intel, like the one you have in your laptop, probably. Then the accelerated part that has NVIDIA GPUs. And then we have and NGT is next generation. I don't remember. Next generation, whatever. It's the next generation partition. GPP is general purpose processor. This will be based on NVIDIA Grace CPU. How many nodding? Okay, some of you knows. And then the next generation technology. next generation technology accelerator, this is still not announced. So it's an installation in 4 steps. The first 2 are already installed, the very big ones. The other 2 that are next generation, by definition of next generation, they're always late. Okay, so BSc, the data center, the 4 research department, we have computer science, earth science, life science, and engineering. Okay, so don't be scared. It's not only operating supercomputer. There are also science around. And now I go to computer science. That is the department in which I work. And I go to, well, here basically you have what we try to do. We have a hardware group, we have a software group, and we have a more like user group that is focusing on performance analysis tools. So tools that allow you to measure things when you run on machines. Okay, so now going smaller and smaller, we arrive to my team. So that is the mobile and embedded base HPC. The idea behind the team is parasites. You know, parasites, they take advantage of another environment to get their life, right? So that's my job. Well, actually, the idea behind the team is, let's see where are the markets that are pushed by other needs, okay, and try to use that in high performance computing. One example is, you are all young, but in the 90s, there was this guy called Bill Gates that wanted to put one desktop computer under each table in all the houses of the world, right? That was one of the sentences of Bill Gates. Somehow, we don't want to discuss how he managed it to do it. So that market increased a lot. There was a lot of personal computers sold in the world, right? That technology was a mass-produced technology, so the price was lowering. So lower price, the HPC guys are saying, hey, maybe we have something that is useful, right? Because we have a computing unit that is lowering the price. We can put a lot of them all together and do a cluster. And that was the first parallel clusters in the 90s. Then the same thing happened in the beginning 2000 with the GPUs, right? So there were gamers. They wanted to have beautiful animation while shooting, but that basically is a lot of floating point operations over the matrices or bits that you want to show in your computer. So GPUs became widely available and very powerful. So price is going down. So let's buy it and put it into a supercomputer. Okay. And also similar thing happened with the ARM technology. And here we are, probably you are more aware of it. So the technology we have in our phone is powered by ARM. It is different from Intel. That technology was basically exploding around 2010 until today, right? Where the market of the phone is basically stable, but till a couple of years ago, it was growing and exploding. So that means a lot of computational power, that basically similar to a supercomputer of a couple of years ago, more than 10, but it's okay. And so take the technology that is becoming powerful and cheap and put it into supercomputer. And somehow this happened with the Fugaku supercomputer. Are you? Yes, I see people. So the Fugaku supercomputer was #1 in the top 500 list until a couple of years ago. And it is still operational, so I don't have to use the past, I have to use the present. It's powered by ARM technology. Okay, so it's the same technology that we have in our phones. Of course, it's packaged in a different way because it's not, so we don't, so it has different packaging, but similar way of functioning. Okay, so in the team, what we do is try to, as I say, parasite, right? Try to take this technology, look at the market, look at the things that are happening around, and test it in an environment that is HPC-like. How many of you are able to launch a job with Slurm on a supercomputer, on a cluster? A lot of you. Good. So the first step that we do, we usually take technology, we mount it in a cluster, we put Linux, we connect some network, we install Slurm, and we run it as a cluster. Okay. So the first thing that we were doing in the past was taking our Android development kits, trash Android, put Linux, and run it as a cluster, okay? And what we are doing, that was with ARM. And what we are doing right now is a similar thing, and what you are going to use this afternoon as a hands-on is very similar. Is development kits of RISC-V that are assembled all together into a cluster, and you write your own C code, you compile, and you submit the job. Okay, that's the idea. What's the difference? That the TRL is different. So the concept of TRL is important. Technology readiness level. Are you aware of it? How many knows about, sorry for the questions, TRL? Couple, just one hand. Okay, so it's a concept that's come from the aerospace, but is applied now to, so we can apply it to several technologies. So to be fast, TRL1 is when you have an idea about an aircraft under the shower. Okay, so it's just an idea. Maybe it works with your engineering skills. It could fly, but you don't have computation, you don't have simulation, you don't have prototypes, you don't want to sit on top of that and fly because it's just under the shower. Okay, so the TRL1 is just the idea, and TRL9 is what we are using right now to fly. So the real product that has been engineered, prototype, tested, validated, certified, and is now sold by companies, and we can sit there and fly. Okay, so that's basically, and there you have different layers, levels, TRL 1, 2, 3, up to 9. Okay, so if we apply this to high performance computing, we can say, okay, hey, I can take the development kit of Android, install it as a cluster, and I can do HPC. Yes and no, right? Because probably at some point I will burn it down, right? If I run HPL for 1 week, a development kit doesn't have a cooling system. So, okay, so we are not at TRL 9, definitely, but we are not even in TRL 1. Okay, we are in the middle. And what we are trying to do is to evaluate. To evaluate technology, the first thing you have to do is measure. So measuring is an obsession. Okay, you have to be able to understand how many flops you are doing, how much time you are spending, how much efficient you're using your system. Okay, so that's why the tools for measuring are very important. Good. Here is going back to the lab, and a little bit is these slides are showing that I'm old, right? So here are the old ARM embedded boards. Then ARM became more like in the server market. So we got sort of server based on ARM. And then in a couple of years ago, we got this that you see, this is the same logo of the sponsor of this school, because here we have the RISC-V technology installed into a cluster. That is the one you are using, the brother of the one you are using this afternoon. And this is an FPGA prototype that we are running nowadays. Here you see there is the nerdy face for pointers to evaluation that we did in the past. If you want, you can find it online. And beyond all this, what we do, just one word, is also an educational experience that is this student cluster competition. Usually we collect 6 crazy students from the University Polytechnic of Catalonia. We train for 6 months, and then we go to Germany to the competition, where we try to compete with this crazy technology with other students from around the world. We never won once. I've been there 10 times. I've been the advisor. You see 10th picture. We won a lot the fan favorite award because we were the most weird, right? So people were coming and voting us, but of course the flops were not our actually first target. Okay, so that's why we call it not only flop. Anyhow, so but that's basically going from Barcelona Supercomputing Center, the data center, the research department, and the group in which we are. Okay, good. It should be 9:30, and I should start talking about RISC-V. I'm late 15 minutes, so worse than the train in Italy. Anyhow, that's the thing that I should not record. I apologize with the people, the trains. Before going on, on RISC-V questions, or with what I presented so far is things that we can discuss in the coffee break as well. Stop me if you have questions. So RISC-V, here I have a question. How many of you knows what is RISC-V? Okay. So now I have another question is, if I say that RISC-V is a free CPU, is true or false? So how many says it's true? A free CPU. Couple of hands, not many. Okay. If I say that is a free instruction set, how many? Okay, good. So that's the first and most important message for the RISC-V of today. So RISC-V defines standard for an instruction set. It doesn't mean that it will give you CPU as a present. Okay. So and now we are going to get there. Good. So what is RISC-V is an instruction set. It has been invented or defined a long time ago in Berkeley. It has been ratified. It's really difficult, right? Because you want to set a standard. If you want to set a standard, you have basically everybody hates you. Okay, and you have to find the way of having everybody half happy. Okay, and so the result is what you have in the slide here on the right. This is RISC-V. Is basically the definition of a couple, I don't know how many, but you can definitely fit it into an A4 page, okay? And these are the basic instructions of the RISC-V 32 bits integer instruction set. That means that with this, you can develop your own CPU that will be able only to operate with integer, only 32 bits. Okay. Here you have the format of your instructions, and here you have the encoding. So if you are familiar with Verilog or VSTL or one of these languages, you can sit down, type your own decoding unit, floating point unit, and so on, and you can write your own CPU. Now, the important point is that you can do that with RISC-V. You cannot do that for Intel. You could, because you can take the definition and type down your own x86 CPU, but you would be illegal, okay? Because the format of the x86 instruction set is not free. You can do the same with ARM, and it would be less illegal, but still illegal, because if you want to do it, you have to ask ARM before to do it and pay them. Okay, RISC-V has the definition is free. You can take the book and do your own implementation. Now the question is, the implementation of the CPU that you are doing based on this instruction, is it free or not? Can you charge for that or not? Yes, you can charge. Okay, so if you do your own implementation, you close the source code, and you can sell it. Okay, that's important. Let's move on. The value of RISC-V is having standards. Probably you are too young for remembering when you were traveling with this. Okay, so every single electronic that you want to bring with you, the Nokia phone, every generation was changing flag, and then you have your own whatever, right? So, and you have to go around with this octopus of connect, right? And then at some point, somebody say, hey, let's do a universal serial bus, USB, and everybody goes with USB, except if you are crazy enough to buy an Apple, and you still are tied to what they want to do because they do not adhere to standards. But that's another thing that I record, but I'm happy to be recorded. Okay, it's not completely true because they are start using USB-C as well, so it's okay. But they've been forced to, right? Because if we have standard, we should be all okay. Okay, good. There is always this I like with this fight in the room. Good. Anyhow, so this is an example, but it seems stupid, but it's not. Look at the technology that we have in this slide, okay? For network, we have standards. We have Ethernet or the 10 gigabit Ethernet. Or so why are we all online now? Because sometimes somebody woke up and say, okay, that router, that access point there should talk this way, okay? And in this way, everybody can build an antenna and communicate. And so we have a standard for connecting our computer. The operating system is the same, right? How can we have so many applications talking with a unified kernel underneath? Because we have these interfaces between the operating system, POSIX, Linux, Windows, and so on. The database as well, you have standard for SQL, MySQL, Oracle, and so on. You have more than one. Yes, okay. Maybe you, in the ideal world, you want only one, but that's important to adopt a standard, define and adopt a standard. For the instruction set, we don't have it, right? We have some of them that are widely used. For example, Intel, we all have probably in the room. No, it's not true because we have an Apple user, at least one. So we are not all powered by x86. We have also ARM in the room, at least. So we don't have a standard there. So I have a short history here of the instruction sets. Right now we have x86. So it's a little bit sad because it's full of things that have died in the history, but it's okay. So Intel wanted to have the beyond the x86 that we have today. They started the 8086, the Itanium, all this architecture. They tried and they failed. Okay, then there was Spark that was developed by a company, then became Spark International. That was sort of a standard because a lot of companies were joining that definition, but in the end, it was the architecture of the K computer. K computer was first in the top 500 before the Fugaku, but then in the end, in 2017, also died. MIPS also was defined. It was sold to Imagination Technology. This is a funny story because in 2013 I was about to find a job to look for a job, and I got the offer for going to Imagination Technology or to Barcelona Supercomputing Center. And I decided to go to Barcelona Supercomputing Center. And after 5 years, there were a wave of people coming from Imagination Technology because they were shutting down the development of the MIPS things, and they were applying to Barcelona Supercomputing Center. So that's the moment in which you think maybe I did the right things, right? Because I'm now interviewing what I could be myself if I would have chosen the other. Anyhow, but that's the story, that basically when there is a company and not a standard behind an architecture, it can happen that that project is shut down because it's not of the interest of the company. It's not good or bad. It's just that the company can turn and drop down one thing that maybe other people are adopting and basing their own job right on. ARM happened the same. So we had a sort of shake a couple of years ago, right? Because at some point it seemed that NVIDIA wanted to buy ARM, and then the deal was canceled 2 years ago. Okay, so this is just to give you an example. So several examples of why having a standard instruction set is important. Imagine that you start today your software business, your software dream, okay? And you start coding based on architecture, whatever. And but this architecture is owned by a company. And in 1 year from now, that company disappears. Your architecture disappears. So all your software effort, or most of your software effort, are basically, well, not trashed, but probably close to trashed, right? So the compiler that you are using disappears or is not maintained anymore, right? So you don't wanna that. So the idea behind the real value behind RISC-V is, let's try to agree on a standard on instruction set. And then every company can do their own business, and they can turn their business and turn down the architecture. But my binary will work on another architecture. Maybe I have to recompile, maybe I have to, okay, but if I have a standard, the hope is that we can uh, um, adopt the standard and the software project can move on smoothly. Okay, that's why, and that's also why the question at the beginning: how many hardware people, how many software people? Because we are talking about one thing that is really in the gray zone, in which there is no hardware or software people, right? So you really have to have, if you are software, you have to have a minimum knowledge of what's underneath, and if you are in the hardware things, you have to, well, implement this kind of things and understand them. Good. Yeah, that behind this when you develop a system on chip fragmentation, right? Nowadays, if you take the chip that is inside here, is not just one CPU. You have a lot of things, right? So you have the camera accelerator, you have the AI accelerator, you have your network modem, whatever. So in the system on chip, you have several what is called IP, intellectual properties, right? That are several times coming from different companies. Okay, so the worst thing you can, so if you open up one of these system on chip nowadays, you can have several instructions set in the same chip. That's crazy, right? So think about it. If you want to program your network chip that is inside your network IP, you have to use maybe a different instruction set that is on the IP that is next to the CPU. So it's really crazy. And the worst thing you can do is start an IP today, sorry, start the development of a system on chip today and say, hey, I have just to do a small whatever microcontroller for the washing machine. Let's define my own instructions. Don't do it. Don't do it. Just take a standard instruction set. Okay. So that's basically the idea. Let's try to homogenize what we have in complex system on chip. And if you have to do a simple thing, still don't invent the wheel, just adopt the standard. Okay. And here I go back to the business model, the question that I was doing before, right? So if you have an Intel microprocessor, the business model is that Intel is doing everything. They are defining the instruction set, they are defining the architecture, they are implementing it, doing the chips most of the time in their foundries, and they sell it to you. So the full chain is covered. That's the business model that we had until a couple of years ago. Then ARM came and say, hey, let's try to do, we define the instruction set. If you want instruction, we can sell you the PDF with the book of the definition, and you can do your own implementation. But you have to pay me a small royalty about this. Every time that you sell a chip, you have to pay me a couple of cents. Right now, there are trillions of ARM devices sold in the world, so they get decent reward about that business. It's not so. Please take me my message well. I mean, I'm not judging this. I'm just pointing you the differences in order for you to understand. Okay. Also, ARM, what is doing is they are developing their own cores. So if you want core, you can go there and put the money on the table and say, hey, I need to do my washing machine and I don't want to do the development of the microcontroller. Still, I want that my washing machine is smart. So they will give you the definition of the core, you do the silicon, and you should define. Okay. And then we have RISC-V that add a little bit more flexibility. It says, okay, the instruction set is open. Everybody can take it. We don't have royalties. Okay. The implementation can be either open or closed. There are implementation of RISC-V cores that are open. One is, how many of you were in Zurich last week? Nobody. Okay, good. There was another summer school about well, in the team of the developing a RISC-V core, and that RISC-V core is open. Okay. We can have several implementation, and as I said, they can be either open or closed, so you can even do business. Good. So we also have the business model covered. Then the ecosystem. You can come and say, hey, man, I mean, even if you give me a chip, I don't mind if it is Intel, ARM, or RISC-V. I need a compiler, and I need something to compile my my software and run it. Yeah, so the idea with RISC-V is that you have this RISC-V International, that is the entity that is controlling the definition of the standard and coordinate the working groups and so on. That is really a work, it looks like a technological government, right? Instead of talking about law, they talk about instruction and bits and so on, but basically it's trying to having people connected and define the standard, the law that are guiding the RISC-V development. Then we have the hardware people that are building the hardware. It can be open source course, it can be closed commercial, it can be in-house, so people can do. There are big companies like NVIDIA and Seagate, they already building their own RISC-V course. And then we have silicon providers that they if you go to AliExpress now, you can buy your own RISC-V core for a couple of dollars. Not nice for HPC, by the way. And then you have the software. So you have the compiler, you have the GNU compiler, you have the LVM compiler, and you have also commercial software built for this. Okay, good. I see that you are getting tired. So stay with me with a couple more slides, then we do a short break, or you ask me questions. There are people around the world that say, hey, RISC-V is like Linux for software, but for the hardware, right? Linux did the same. It is free. You have now a free operating system. It's open source. Everybody can take it. And not true. Okay, not completely true, because if you look at the software, the flow of development for the software, okay, you have to develop the Linux kernel, and we all thanks Linus Torvald for doing that first job, okay? And then you need a compiler, you compile it, and you use it. Costs of this formally zero. You need a laptop, probably for work on it. You need a tons of hours of manpower, okay? And that's also thing that have some price, right? But physically speaking, you don't have to pay anything, right? If we jump on the hardware side, you can do the same. You sit down, you write your own CPU, the definition of your own system on chip. But then when you want to do the chip, you have to go to a foundry that is doing the silicon, okay? And that's a lot of money, okay? And then you can use it. So don't say that it's the same, because it's not the same. There are a lot of money involved that are flowing in a different way. I'm not saying that that software is for free. I'm saying that the money are flowing very, very differently in these two cases, okay? And this also affects the way in which we develop. That's important for the prototypes. The right side of this slide, so the hardware is very slow. We can define today a very nice architecture if we want. But from this room to the moment in which I have a chip that I can use and boot Linux, we have at least 1 year of nothing. Technical development meaning, but nothing, which we cannot really work on that architecture, okay? Good. That's just the summary. So why RISC-V is an open standard instruction set. It allows to homogenize the definition, the design of system on chips. It defines a new business model, as we said, Intel, ARM, and RISC-V. And it is not dependent on market fluctuations. Okay, this is something that I didn't comment much, but basically, if you have a standard that is, especially in these days in which we have fortunately wars going on, and also bans. So tomorrow the US can wake up and say, I don't sell any more Intel chips to Europe. What do? We will not have laptop anymore, right? And this, it never happened to Europe, fortunately, but it happened with other countries. So that's another reason for having a standard that is adopted world, okay? Here you have a presentation of Krista Zanovic, that is the one of the big brain behind RISC-V, that is talking similar. Actually, I was heavily inspired by this video. It's very nice. It's a talk that I was attending in the US, and it's really, really nice and interesting. Before jumping to this topic, questions, things that are not clear to you, tell me. Otherwise, this is ChatGPT, not used. I mean, actually, you can open the video of Krista Zanovic and look at it, and it's in YouTube. Is it something that you don't get it, or you want to ask, or doubts? Yes, please. I know that there are projects in which Intel is adopting the RISC-V instruction set. Yes. So here there is a law of market that's probably, if you will drive a company at some point, I don't know if you drive a company, I don't want to offend anybody in this room, but one thing that I learned, I never draw a company, I want to do that, I would be a disaster in that. But what I understood is that if 99% of your customer are using your products and you are changing the basement of your product, you don't want to tell your customer. So that's basically right. So if you have everybody buying x86 architecture and happy with the compiler and VTunes and all those kind of things, and you are working underneath to change this, you don't want to tell the customer, because basically you are scaring your customer. So there is no technology in this sentence. It's just one psychological thing. So, but it's true that we talk with NVIDIA, we talk with Intel, and everybody in the world, I would say, knows that they are looking into this. Maybe they are not looking into this for the high-end Xeon CPU for the next generation. Maybe they're using it for the microcontrollers. Or, for example, Seagate, they were one of the first using microcontroller for their hard drives based on RISC, and nobody is crying. I mean, you use Seagate's drives and you don't even know, right? So the answer is, I would say most probably everybody's looking into it, my feeling. Maybe not with their main business, but the real answer is that we will never know until this will happen. So maybe, you know, that the x86 instruction set in reality is just one thing that they present to us, but behind it, there is always sort of translation of micro instructions and these kind of things, right? So at some point, maybe we can even have the switch to RISC-V and don't even realize it, right? so now I don't want to do the theory of conspiration, but I mean, I think that a lot of people are looking into it because there are benefits. Yes, please.
Very brief. The first one is so the question is which kind of the
Yeah.
our perspective, we kind of we can
No.
so it's but I just want to close the parenthesis. And the second thing is we had a slide on the
Yes.
that those are 2019.
Yes, it was not. It was not a drop. It was. This is part of. No. It's just a matter of the openness of the instruction set, and also sort of the interest of the whole community. You know that these research centers are also driven by um, what's called public funding. Okay, so when we started talking with the public institution funding the research project, we started saying, hey, I mean, we should It was in the age in which the first wave of Trump and so on, in which they were banning things, closing things. Okay, so also ARM was sold to Asian holding. So basically, there were a discussion, still little technical, more political and sociological, and say, hey, probably we should turn into something that nobody will lock us into that technology or the other. So that's why, but I mean, in the lab, we still have both of them and we are still working in both. Good. So yes, please. The mic. Otherwise, the recording, there is no, I should do a summary of the question.
Okay, can you hear me? Yes.
Yes.
If you can expand a little bit between the interaction between RISC-V and the other layers of implementation. I mean, mainly between RISC-V and the software, there is firmware in the middle, I think.
Yes.
And so if you can a little bit expand about firmware interaction with RISC-V, just for the one that are not on the field of these topics, I'm a mathematician.
I suggest, I don't want to turn down question. It's very unpolite and not nice, but I have more details about it because the idea was just to give the general idea, and then we drive into the prototype that we have, and there I think you can get the idea. So if you're patient, I think we are going to hit that before 1 when we finish. Yeah, sorry, but we will look it because we have a couple of draws and things that will allow us to understand that. Move on. Yes, how different is RISC-V compared to other instruction sets? Here I go fast. The important point is the difference between an incremental ISA and a modular ISA. Okay, incremental ISA means that if you come with a new release, you have to maintain all the old instruction plus the new ones. So every time that I come with a new nice instruction, I still have to maintain the old one, right? So the Intel instruction set is right now suffering a lot of this, that you have a lot of legacy. Now, if we work on RISC-V, we can just say, hey, we're very lean, of course, but we have something like 10 years, 5 years experience, right? While Intel has maybe 20 years of development, right? So it's unfair to shoot against the complexity of Intel because they have a lot of history and RISC-V doesn't, right? But conceptually, there is one difference between incrementally evolving the instruction set incrementally and make it modular. The idea of RISC-V is that I give you the A4 definition that I show you in the first slide, couple of 20, 50 instructions, and then I give you extensions that you can plug in. And if you need that extension, you implement it and your CPU will be compliant with that standard. If not, you leave it and that's it. Okay. And here you have basically the standards. Yeah, here you have the base instruction set. The one that I showed you before, it was the 32-bit integer. You see 49 instructions. And then you have the extensions. Okay, everyone has a letter, and the one that is going to be interesting today is the V extension, the 186 instruction added. Okay, so that's basically what we are adding on top of the basic instruction when we do a vector CPU. This is what we are going to see later. But the basic idea here is that we don't need to be incremental, we can be modular. Okay, that's the message. Code size, well, this is something that I prefer to skip. I mean, because we are late, right? So, and I want to arrive where things are more interesting. Here I try to give you the message that the code size compared to other architecture is smaller with RISC-V. It can be faster, and the documentation size is usually smaller. But all these, I think that is a selling point that I don't need to sell to you, right? Because the RISC-V infrastructure is young, so it's natural that we have less documentation somehow, right? So it was just a way of showing you that this has been measured and is being controlled. But let's move on with that's nice. I don't know if you know the compiler explorer. Have you ever used? Okay, so if you go to the compiler explorer to this QR code, you have the sum of a vector compiled with different compiler, and you see that if you put minus O2 as standard optimization flag, you basically have identical, well, the same number of instructions with different architectures. And yeah, you can check the difference of the syntaxes, but basically with simple code, you don't even recognize the difference. Okay, so, but we will jump into codes in which we will see the difference. So, but yeah, I wanted to leave you this example so that you can play later tonight, or if you have to submit anything for having your credits, look into that. Okay, the idea was to be here at 10:15, and I'm getting better, eh? And jump to the data parallelism. This is a good moment if you want to take a small break, or so something like 2 minutes. I don't want to do a break of half an hour, but either ask question, stand up, do a turnaround, because otherwise you fall asleep. Okay, so give a little bit of break. Posso aprire? Sì? Non c'è l'allarme. Ok. Ci servirebbe una sedia. Sa, tienimi aperto, perché sennò perdete il professore. Io prendo una sedia, ce la metto in mezzo. Adesso è quando chiudi e dici sono troppo contento di aver perso il professore. Passa. Ah, ok, ok.
Questa è la ventilazione.
Ah, ok. Lasciamo chiuso allora? Ok, good. No, it's okay, it's okay. Thank you. Sorry. I was joking that keep me the door open. Otherwise, you lose the professor, right? Hanno detto che hanno acceso la ventilazione, quindi meglio lasciare chiuso.
Per l'architettura che è modulare. Questo se ne parlerai.
Okay. Can you? Hey, hey, hey. Okay, so in the first part, we tried to add a little bit of background about the RISC-V. Okay, now a little bit of I mentioned a lot of time this vector thing, vector whatever. I don't know if you are familiar or not, but basically the idea here is to have to exploit, if you've been in a course of computer architecture, the data level parallelism. Okay, so here there are 4 paradigms. So let me try to give you 1 minute of introduction. So you can have one instruction and operating on one data, right? That's basically this side of the plot. Then you can have multiple instruction operating on a single data, that is MISD, multiple instruction single data. Okay. Then this, if we go on the right, if we go to the bottom, we can have SIMD, single instruction multiple data. So you issue an instruction, you operate several data. And then you can have multiple instruction multiple data. Okay, so you can have multiple instruction flying operating on multiple data. So you see the matrix, right? So if I move to the right, I add multiple instruction. If I move to the bottom, I add multiple data. If I combine both of them, I have multiple instruction, multiple data. So what we will talk today, mostly today, is this one, SIMD, single instruction, multiple data. Okay. Now my question is, are you familiar with SIMD instructions? So do you know what they are? So how many have zero idea of SIMD, of zero idea? Okay, okay. Just a very quick thing. It's a question or no? Okay. So, is it a question or you just saying? Okay, you just declaring your not knowledge. Okay. So you know about instructions, right? So you have your binary, you have your instruction that are basically different types of instruction. You can access the memory, doing arithmetic instruction, branches, and so on. Let's focus one moment on arithmetic instructions. Okay. So if I have to do an add, okay, if I have to do an add, I can do a scalar add, okay, the typical instruction add. I need to fetch register A, register B, so allocation of memory where I have the data A, then the data B, then I put it in my register, then I sum the two registers, I store in another register, and then I do the memory access to store back the data, right? Load, store, that basically Hennessy Patterson 101, okay? Good. So now imagine you can do this instead to do it only on one data, do it on multiple data. Okay, so I always do adds. I cannot do anything else. Okay, but I can do it on multiple data. So I can go to the memory, fetch, tell me a number, 17 data. I'm just putting crazy numbers. Okay, I fetch 17 data, I put it in my register, and these are the data A from 0 to 16. And then I fetch the other 17 and I have B, and then I apply the add over these two registers. And of course, I will need functional units that are able to operate multiple data at the same time. So I need more functional units, or I have to pipeline these 16 data. That's a matter of implementation. Usually you have as many functional units as we will see that what I'm saying is not true, but usually in the Intel one you have. And then you have the result and you store it back. That's what we call vector computing, or SIMD, single instruction multiple data, right? So single instruction operating on multiple data. That's, I think, everything you need to know today. Which example do you know? How many have been working with the AVX 512 in the room? With intrinsics, typic intrinsics in the... Wow, okay, good. So we have macho programmers. Good. So here is what I was describing. I didn't remember that I had this. So here in a scalar mode, you have A and B, and you sum it. If you have a SIMD mode, you load. Here I have better number from 0 to 7, so 8 data. Why I'm putting an example with 8 data here? Because the AVX 512, that is the most common SIMD instruction set that we know, that is the Intel one, is able to operate 8 double precision elements at a time. Okay, so you do a load and you load 8 data on your register. Then you do the other loads, and you have two registers that are full of data that you need, and then you operate the add, and then you have the result, and you store it back. Here I have the black is not really read it. Can you read it? The black box? Yes, good. That's good. So how many knows about this RISC-V? RISC-V is okay. Yeah, it's the most basic function that you can have that is operating on a vector, right? So you are doing a constant multiplied by a vector x plus the vector y, and you store it back to the vector y. That's basically the what we call the algebra kernel. Okay. Now, if you see it, the loop here is really something that is it looks like perfect for this kind of computation, right? Because there are no ifs in the middle. So if you have if x is very big, you can really take advantage, x and y, I mean, you can really take advantage of operating it 8 by 8 instead of 1 by 1, right? So which hardware implementation for SIMD do you know? Well, there are SIMD and vector architecture. We will now try to understand the difference, and the GPUs. Okay. The example that I will stick to are the x86 Intel that we have nowadays. Each core has a SIMD unit. Well, these are sentences that were sold by Intel, so that the SIMD unit width will double every 2 years. No, every 4 years. This is definitely not true. Okay, they started. I have a slide here. Let me go here. They started with the yeah, with the green one, that is basically MMX, the extension that we're using 2 doubles at the same time, and then they put 4 doubles, and then they put, no, sorry, there was first there was 2 floats, then they put 2 doubles, and then they put 4 doubles, and then they arrived to 8 doubles. That is the 512 bit. Every double is 64 bit. If I multiply by 8, I have 512 bits. Okay, so that's good. And that's the extension that we have nowadays. So this, actually, there are architectures that are going back to 256. And instead of having one unit operating 8 elements at a time, they have 2 units of 4. Okay, so that are independent. Okay, it's slightly different. Anyhow, let me go back. There is not only Intel, there is the, I'm a little bit lost. Yes. So ARM has, yes, please. Yes. Yes. That's a very important observation. Thank you. I'm assuming in all these sections until the break, I'm assuming single core. And actually that's my problem, because I'm doing exascale right now with a single core at 50 megahertz. That's ridiculous, okay? But it's fun, let's say. But yes, we are looking into the performance of a single core. Then we can scale the number of cores. But that's another. There is not actually data level parallelism is another kind of. So in ARM cores, we have the Neon extension, and we have the scalable vector as SVE, scalable vector extension. And then in IBM, we have this vector scalar extension as VSX. And then we have this NEC Aurora, NEC. Anybody knows about? Maybe you know because you have the air conditioned by. They are huge, and they're Japanese, and they are huge, and they also do high performance computing, and they do an accelerator that is based on a SIMD, a vector machine. Okay, so here is the history. I already told you, and here is the example of coding. I mean, we're more familiar with code than with other stories. So let's jump into a code that is easy to understand, okay? If you don't see it, let me do this way. I hope you can see. So this function is the same that I showed you before. It's the standard scalar one, okay? Then here I put the main. I put the main because it's important, okay? Let's assume that I have 32 elements for each vector, okay? 32 is nice because it's a power of 2, right? And also it's a multiple of 8. That's nice as well, because if I have a vector unit that is operating 8 by 8, well, I can write down, now I zoom, sorry. Good. If I operate 8 by 8, I can put the intrinsics of the AVX 512, okay, that are actually here. I'm load into the register. Sorry, I'm passing the pointer, right? And I'm storing it into xvec. Then I'm loading y. Then I'm doing the fuse, multiply, and add, okay, of x and y, and the constant is alpha. Before doing this, I didn't prepare. You have to think that you have to prepare your data into vectors, okay? And now I prepared x and y, and I have to do alpha multiply x plus y, and I remember, okay, I didn't prepare alpha, right? What I have to do with alpha, I have to do a broadcast of the same value, right? So that's basically what I'm setting is an equivalent of broadcasting the same value that is alpha. I'm putting it on the 8 elements, okay? So now I have 3 registers, x, y, and alpha, that are ready, so I can operate them with the fuse, multiply, and add. That is one instruction that is doing alpha times x plus y, okay? And I'm storing it into result, and then I'm doing a store that is a vector store. Is not a scalar store. So I'm taking a chunk of 8 data and I'm putting back to the memory, okay? And that's basically the same code that you have here on top, that is written scalar, but is written with vectors. So tell me benefits and drawbacks of this implementation. Come on. You are software people. Most of the people are software. So tell me good and bad things. Should. It's a little bit more complicated, yes. But it's much faster. I agree. Yes. Especially with this kind of function is times 8 faster, I would say. Length has to be a power of 2, completely true. What do we do if the length is not, no, sorry, multiple of 8? Multiple of 8, yes. What do we do if it is not multiple of 8? Sorry? Pad. Yes, or we do scalar. With the rest of, I mean, if we have to do 10, we can do a vector of 8 and 2 iteration of scalar, right? So that's another. Somebody was saying something you wanted, yes. Correct. Correct. And you are going in the direction of, somebody has already said, cache. Exactly. We are so we are shooting a lot of data against the cache. I don't want to say polluting, but sometimes we are polluting the cache, right? Imagine that you have this vector that is not 8 elements but bigger. You can arrive to, you have to bring all your data into the cache at some point, and you are wiping out everything you have in the data every time that you do an iteration. So sometimes it's good, sometimes it's bad. For the cache, you have to be careful. Yes, please. You mean that if I use this kind of instruction, automatically the CPU can lower the frequency, right? Yes, that's true. That's true for for the Intel implementation. So in Intel, when you use these kind of things, you either burn the chip or you lower the frequency, right? Why? Because you are activating all the functional unit you have. So you have a lot of silicon into one spot, and you are activating everything. If you run it at turbo boost, you are melting down because you are creating a hot spot in your chip. So you have to lower the frequency in order to be able to. Still is beneficial for performance, because imagine that you halve the frequency, but you gain a factor of 8. You still have a factor of 4 of gaining, right? So it's a gain. Nobody told me you are software people, but you are always running with Intel. Nobody is telling me, right? I'm losing portability. The code on top, I can compile it everywhere, right? The code on the bottom is really locked into this kind of implementation. Okay, so that's very important. Especially this is the kind of things that I invite you for the whole life, your technical life. Take always into account the portability. It's better to lose something in performance and keep portability than the opposite. Always. Even if you now think that you will be able to speed up everything at a single bit, at some point somebody will suffer for your choice of putting an intrinsics, okay? Why? Because I suffered that because I received a lot of this code, and I have to run it on ARM 10 years ago and on RISC-V today, and I have to go back to that implementation on top. And sometimes people are throwing away this, the one on top, and just keeping this because everything is Intel, right? But it's not true. So keep always in mind the portability. Good. So let's change the 32. So we were talking about, this is one possibility for solving the, if this is not 32, if I have a number that is not multiple of 8s, well, I will do the same implementation with my vector intrinsics, and I will add what is called a loop tail, right? So everything that is not multiple of 8, I will do it scalar. It's okay, slow but steady. Good. Any other comments on this code? Yes, but if I have to operate 3 elements, it's always like, right? So but it's true. We can do a sort of even more complex implementation in which we can check if what is left over is 4. I can use SSX, MMX for one of the other extension of 4 elements. Right? But yeah, it will make the code more and more complex and less port. But that's true. What else? What else do we need to? Yes. 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 So, so what you are saying is that, let me try to understand if I understand correctly. So you say, instead of doing a loop that is looping over the whole vector and just do this operation, try to structure your code to have a body of the loop that is more bulky, so to do more work. Right. Do you do GPU programming? Or so that's the idea of the kernels of the GPUs, right? So you want to have a little bit of work to offload to the GPU, right? Yeah, it's true. It's something that it's beneficial in both the GPU world and the vector world. But still, there is one thing that I wanted to tell is not in this slide, but if you have a smart enough compiler, a smart enough compiler is able to auto-vectorize this. Okay, so the compiler goes through the loop and sees that you are operating without ifs. You are operating on safe data that are not, for example, global variable or something like this. And the compiler is able to generate a binary that implements this, but the source code remains this. And that's the key point that you want to have, right? So you want to write code that remains portable and have, say, auto-vectorization. Sometimes it's not possible because the auto-vectorizer is automatic, and sometimes it's not. He has to do assumptions. Okay. Sorry? Exactly. Exactly. That's a very good point. We are jumping something like half an hour further in the slides, but yes, the three ways of having vectorization are from the less desirable to the most desirable is you put intrinsics, bad. You put pragmas, that is what you were saying. You can put a pragma and annotate with OpenMP, say, force, please compiler, try to do this. And in the pragma, you can also say, I know that you are worried that this variable can change. It's not assume safe, right? And so you force the compiler to say assume safe, and then maybe something explodes, but or you get the wrong. Exactly. So you're giving instruction to the machine. And the last one is the most desirable one. That is what I was trying to say, right? So don't put anything, just activate the auto vectorization. These are the three, bless you, three way of operating. Now, let me jump to one more elegant vector way of handling vectors. That is the one that is introduced in RISC-V, but it's also present in the ARM extension. Okay, this is a way to handle vector tails. Okay, let's assume that we don't have an instruction that is fixed. Okay, but we just have the maximum that is fixed. Okay, so I can operate a vector that is up to 8 or up to 4. Let me use 4 now, because in this image I was smart enough to do 4 instead of 8. Anyhow, so I can put VL, the vector length, I can put it to 4 and operate to 4. And then when I have a tail, I don't operate scalar, but I just can redefine the vector length to the size that I need. Okay, and here the implementation becomes more and more elegant because I don't have the tail anymore. Okay, so I do the broadcast of the alpha that is now 8. Sorry, I have small incoherencies here, but anyhow, you are smart and you understand. So I set the vector alpha. Okay, then I enter the loop, and the first thing that I do is this setting granted vector length, GVL, granted vector length. What this GVL is an instruction that, as a programmer, I'm sending to the CPU, and I'm telling the CPU, hey, give me the maximum vector length you can give me. Or actually, I can tell the hardware, give me that size of vector. And the hardware will return to me the maximum that he can do. But if I can tell him, give me just less than the maximum, the hardware will configure itself to operate on that vector length. That's great, right? Because in this way, every time that I enter the loop, I can say, hey, give me 1,000 elements, and the hardware will tell me, no, I just have 4, I will give you 4. And I operate with the GVL. GVL, you see that is always part of the two loads, and is part of the multiply and add here, and is part of the store. So this is an extra parameter that allows us to work with a different vector length. We have a maximum, of course, because we cannot have an infinite vector length. Okay, the implementation needs to have a top. We cannot have a football court of silicon to have infinite vector length, right? But we can do variable vector length, and in this way, we can avoid the loop tails. Okay, so yes, please. Yes. The real answer, so the short answer is the latency decreases, but it's not linear. So if you are using half of the data, you are not spending half of the cycles. Okay, so you're spending more. Okay, so it's always undesirable to underuse your vector. Okay, if you start using vector, you always want to fill them. That's the mess. But yes, is less efficient, but it's still is efficient. The long answer is it depends on the implementation a lot. Okay. And also there is another important observation here is that, and that is that from the point of view of the efficiency in cycles is one point. From the point of view of the power consumption is another point, right? Because if I can, when I operate these two elements, I can completely switch off the other two. I'm saving power. And this is completely or almost completely on the implementation. But it's very important. Vado bene, no? Sì. Good. Other questions? Wow, a lot. Good. Thank you. Let's start from the bottom that she was first. Correct. No, it can be what. So we can put here a prime number if we want in GVL. It's not a problem. Other questions? You. No, it's here when GVL is 1, the compiler is always smart enough to say you're fooling me, I go Scala. Yes.
And my question is that are they different for output?
Sorry, are the addresses?
They
Yes.
that now
Mm-hmm. Yes. Yes, yes, yes. So for having this, yes, please. Yeah, now I'm thinking. I'm not completely sure if you can catch it or not. It's not, yeah, but so the you want to comment something on this or? Yes, so what you are saying is true if you are not in -03. In -03, you usually you have, I think, just one implementation that is the one you use, and you hope for the best. So, but yeah, I think that all of you have right that at compile time, I cannot assume a value about this. It can be any value. So I cannot say if it is one, go for another path. So probably what I said is stupid, and probably if you have a GVL that is equal 1, you are going through a path that is, say, less efficient. One-fourth of efficiency of the one you can have. Still, I don't know if there is some other tricky place in which break.
Yeah. Go.
We have to go. Let me check what. One word, because nobody told me about masks. What you can do instead of doing scalar tails, like I was doing this, I can also do, well, actually, somebody was saying I'm going to pad, right? Pad data means I always operate multiple of 8, and then I trash the part that I don't want. And usually I do mask for doing this. So in RISC-V, we have the support of both the variable vector length and the masks, okay? That's very, very nice. Scalar versus SIMD, well, this we will see later. Don't worry. Please enjoy your break. Okay, let's restart. Let's try to restart. Please take your seats. We have still 90 minutes before lunch, but it's real. I mean, it's like we did so far. Okay, so I hope it's enjoyable. So yeah, I mentioned we have vector length and masks. Okay, so variable vector length and masks. So we restart from here. Okay. This I jump it because I want to be. So I was talking with some of you during the break. So which kind of accesses to the memory we do have? Okay, so we in at least in RISC-V vector we have strided or say indexed. The strided can be unit strided. That means that I'm accessing a contiguous area. So the stride is 1, okay? So a contiguous area of data. Here I'm continue using the idea of the vector length equal 4, okay? So stride 1 means I'm going to the memory with a load, and I take a memory buffer that is equivalent to 4 elements, and I bring it to my register. Then we have a fixed strided that is a number that you can use. For example, here I'm taking a stride 2, so I'm taking 1 every 2 data. Here I'm taking a stride 8, so I take 1 data, 7 off, the 8th, and then the 16th, and so on. Okay, so that's the 2 types of accesses that you can have. There on the left side, you have the intrinsics that you can use. But as I said, it's important that you know this mechanism, but hopefully I wish you not to have to type in this with the left part of in your code, okay? Because so that your code will remain portable. Then we have the index accesses that are, say, gather and scatter. I don't know if you are familiar with it. It's important to understand it for something that I'm going to tell you later. So you can provide a vector with you can provide to the memory unit with a vector of indexes and a base address, and you can load data that are corresponding to the indexes that you are passing. So it can be, say, an arbitrary pattern of accesses. Okay, so if you think it could be very useful for if you have a stencil, for example, and you have to gather data at different distances. So this kind of accesses are very useful. Okay, there is a drawback that is the implementation, right? So if so, how much cycles do you expect they will take these 3 kind of accesses, right? We have the unit strided, the constant stride, and the indexed. Do you expect that they have the same performance? No, right? When I do the indexed, I have to do the calculation of the indexes. I have to go to different area of the memory for probably I will suffer misses in the cache. So can be tricky, right? Yeah. That's important. So this is implementation dependent. That's another nice feature, is vector chaining. Okay, so imagine you have this sequence, vector loads, multiply and add. Okay, so I load the data in the vector 1, then I multiply vector 1 and vector 2 and I store it in vector 3. And then I add vector 3, vector 4, and I store it in vector 5. You see that I have dependencies, right? So according to the logics and the strict rules of load store instructions, these should introduce bubbles in my pipe. Well, actually, I have to finish the whole load of vector 1 before starting the multiplication. So let's look in this way. That is easier, right? So I cannot start multiply the data before finishing the load, right? But we know that the vector is formed by a lot of elements. Okay, so somehow, as long as I have some data loaded, I can start working with the multiplication without waiting the load to finish, right? Okay, this is true only if I can operate a subset of data of my vector. Okay, otherwise I always have to wait to finish the load, to finish the multiplication and the add. So you see the difference, right? I'm operating. Are you getting it? Should I repeat it or is it clear? It's clear, right? Yes, please. Is similar, yes, but here is, say, more structured in the architecture of the processor. But yeah, the concept is the same. So you are doing a load of several data, let's say X data, okay, bringing the data from the memory to your register. As long as you have a subset of this X data loaded, you can proceed with the next instruction. Okay, that's basically the concept. Yes, please.
Prova?
Yeah.
Is it the same reasoning, the same scheme that we use, for example, in the online softmax for the transformers, that we use only a batch of examples from the queries and keys for the transformer architecture, and then we have iteratively update the softmax value, because it's pretty similar also in terms of tensor product with multiplication and then addition. So
yes, so yes, so I'm not strictly familiar with what the kernels that you are mentioning, but the basic concept is always, as long as you have the data that you need for the operations that follows, you can start. That basically, I guess, what you were mentioning about the.
okay, because we didn't study this in.
Yeah. No, this is sort of advanced architecture, but is so really try to get the sense of the picture. So instead of waiting for an instruction that is taking a lot of time and starting the following one, you can compact them and overlap them. Okay, that's the important point. Why are we overlapping? So sorry, we are overlapping is easy because we want to be faster, right? But we can overlap because the multiplication is actually using the floating point, so say the functional unit, while the load is using the channel to the memory. So we are not using the same resources. There are different resources. One is the load store unit. The other one is the arithmetic floating functional unit. Okay. Yes, please.
Hello, hello.
Yes.
Okay. How, in this case, is the synchronization between components inside the microarchitecture managed? Because I suppose that there is not a single clock in this case, like in a simple microarchitecture, because you have to manage different components at different time scales.
Yeah, but the clock is the same. So let's look at this. So this is the putting all together, right? So that's basically everything that you see here, except the main memory, is working at the same clock frequency. So at least this is synchronous. Okay, so it should be fine. The synchronization should be fine. Okay. Let's move on, because it looks everything perfect, right? But it's not, and I want to explain you why it's not. It's with some of you. I already commented this in the break, but so first of all, we need a compiler to meet vector instructions, right? So we can rely on GCC. GCC is able to emit some vector instructions. Some of you are suffering that. I wish you a nice and good recovery. Then there has been the different version of the vector RISC-V vector extension. Okay, I told you at the beginning that we have the core of RISC-V instructions plus modules that are extensions. Okay, yeah, but the vector extension has been launched with version 171 in June 2019, and then has been updated for the 2 following years. Okay, so we started, for example, in the project in which I work, we started working with 071 in 2019 because it was the only one available at that time. But in the meantime, the instructions has been so the whole instruction definition has changed. Okay, so now what we have to do is we have to update our hardware for following the version 1.0. Bad news, we have to thrash a lot of work and update it, say, not thrash. But the good news is that the version 1.0 has been ratified and should be stable for the next years. Okay, so the committee that is behind decided, okay, this is really the vector extension we want. We stay with 1.0. So if we build now with 1.0, probably we are building on top of something that is stable. Please, question. I think yes, somehow yes, but it's also, I think we are suffering we were, how can I say, we were too enthusiastic with 071. I mean, when we started developing with 071, we knew that there were a committee working on the ratification of the following versions. So we knew this would happen. Yes, we were aware. Yes, yes, definitely, yes. And yeah, the hardware implementation is tied to a specific version. Okay, right now I'm talking about something that I already that I still didn't explain to you, but it's going to come in the next hour. In the project in which we are working, we have hardware with 071 and up and running, and then we have some prototype 1,0 that is running stable, only the scalar part, and then when we start adding vector instruction, we are in the debug phase. So 1,0 is almost there. Okay, I could give you an account on 071 today, and you could log in doing SSH without any problem today. I could not give you an account on 1,0 today, just for you to understand the level of okay, so everything is definitely not perfect, as you can see. There is still work, a lot of work to do, okay? Performance analysis tools, do you have questions on the RISC-V things, on the vector part? Otherwise, yes, please.
About strided memory access.
Yes.
So the indexes are calculated by the CPU or by the memory management unit, and how does the performance there works?
The indexes are computed in the I mean, computed, what do you mean? I mean, here we have
the assembly instruction to load there are like a specific instruction,
yes.
or so there are like a specific instruction that are implemented. Yes. So I do not load the single like cell of memory, but there is an strided loading instruction.
Yes.
Okay.
Sorry, these are the syntaxes. Yes.
Okay.
Where
so
you see
small.
Yes.
Thank you.
Now I can anticipate a little bit one of the problem of this kind of architecture, right? Probably you already see it. If I want to, now we are talking about 4 elements, right? But let's assume that we want 4. So we have a vector that is very big. So I don't know, 64 double precision elements, right? In our implementation that we are going to see soon, we have 256 double precision elements. Okay, it's huge. It's 32 times bigger than the one that has Intel today. Okay, what's a key feature for the access to the memory? That we need to be able to send a lot of requests to the memory at the same time in order to saturate as much as possible the bandwidth of imagine that you have to do a load and you have to load 256 double precision elements. Okay, if you are not able to generate a lot of requests, you are wasting a lot of time in sending requests to the memory and bring your data back and say building your own vector in the register, right? So that's one architectural feature that your load store unit needs to have to be able to shoot a lot of requests to the memory very fast. We will go back to this. Let me introduce one moment the performance analysis tools, because it's really something that you are going to see later and you will need also this afternoon in the class of Andrea. So let me take it from far away. So why do we need the tools? Because we are doing science, right? So we are doing science, so we want to measure things and we want to be able to repeat experiments, continue measurement, compare the measurement, and understand that we are able to reproduce the result of the experiment that we are doing. Okay. Also, we want tools because this is very important, because it's important for lawyers, because if you have numbers that you measure, you can choose somebody and say, hey, I blame you because this data is telling me that the memory is slow and you are the producer of the memory, right? So and also it's critical for system architects because they need to understand the system that they are building, because there are several occasions in which we develop or we think that our architecture is beautiful on the blackboard, but then when we implement it, we measure things and we discover that we have this or that feature that is actually not behaving as we foresee. Okay, so we really need these kind of tools to understand what's going on. And which are the great, beautiful tools that we have to measurement? We have telescopes going to space. We have Large Hadron Collider. We have beautiful labs in biology. And what do we do in computer science? We put printf, right? That's good. We are advanced, right? That's the thing that we should not do. So don't draw conclusion from the integral of a function, but look into the behavior of the function. Okay, so we as the other field of science are evolving into better and better measurements, we also have to do that. Okay, so that's why performance analysis tools are very important, and we cannot just do printfs and put a get time of day at the beginning, at the end of our main to understand. Good. Okay, so how many of you are familiar with perf? Good. Okay, that's so I don't have to. So most of you know that there is this tool that is almost embedded in your Linux distribution that is able to access the performance counters, monitor the CPU cycles, the instruction, cache hit miss, and so on. It can profile your codes, so it can tell you which function are using more time, and can do also some tracing and some statistical analysis. Okay, so this is a very smart example. So here I was tracing a sleep one on Mare Nostrum. So that's a bad use of a supercomputer. Okay? Don't do that. But it was 1 second, right? And that's the typical things that you can have. Okay, so you have several metrics that you can use in order to, I don't know if it is visible, but so how many instruction of which cycle or which type, and then cycles and these kind of things. This is useful as a first level, say, if you want to understand a little bit how your code is behaving. It's also useful this afternoon for the, I think for the hands-on that Andrea will show you. It has some limitation though. Can you see one limitation? Sorry, I didn't. That's not a, that's the good feature, actually. No graphical interface is a good feature, actually. Thanks, thanks, but no. Tell me.
It's fine. So recording the data takes a lot of time, and will.
There is exactly there could be a problem of interference between the measurement and the run itself. That's true. Still, the overhead can be negligible. So we need to know. We need to know that can interfere. Yes. Exactly, unless you start instrumenting your code. And as far as I know, it's just scalar, right? You cannot perf something that is parallel, or at least you cannot monitor with perf with a multi-node run, right? Because perf lives within an instance of Linux. So if you get out from the one instance of Linux, the number that you are getting, yes, please. Exactly, and you don't have GPU support, exactly. So that's why it's okay for, say, a preliminary analysis, but then there are other tools. If you go parallel, of course, I come from BSc, so I have one slide about the tools that we developed at BSc. There is Extrae, that is this tool that is able to hook into different events. Let's assume that you have an MPI program, okay? Every time that you enter an MPI program, we can collect data. Okay, so we can intercept the MPI call and collect data. For example, some hardware counter. Okay, and we collect all these into a trace, and then we have a visualizer that can show you what's going on, and is something that questa è l'aria, vero? So here there's the typical example of a scalability test, right? So you have 48 threads in the y-axis, and you have time on the x-axis, right? And with different color, we represent whatever is now is not relevant, but basically changing the number of MPI processes from 48 to 96, 192 to 288. Well, there is one more here. You see how your code scales, and you can also see how your code is unbalanced here, right? I mean, you see that there are phases of your code. Sorry, too much. Yeah. So here you can see that here there are things that are lasting less than the other blue, right? So you can start digging into your execution with this kind of tools. Anyhow, so then you can get MPI profiles. So how much time you are spending in each time of MPI send, receive, and so on. And you can have the connectivity patterns like so if you have here you have your MPI processes, and here you have your MPI processes, and you have one dot every time that you send data, and the color is telling you how much data you are sending, these kind of things, okay? So these are a little bit more insightful than having just a get time of day, and it can work on multiple nodes, okay? Other tools for each PC, here we can do a contest. So how many in the room knows all the names of the first column? All the names of the first column. So Extrae, Paraver, Vampire, Scorpi, Scalaska, Tau, HPC Toolkit, Liquid, VTune, and Performance Repo. Well, no. Just that you heard it. Just that you heard it. Yes. Okay. So, some of you. Okay. Probably VTune is the one that you know more, right? Because it's the Intel one. No. Anyhow, these are the tools, and I tried to summarize here. I'm actually not completely sure that this is completely accurate. If you take picture, don't blame me too much. I was not spent. Yes, please. GPU doesn't exist in my world, so that's why. No, so it's recorded. Yeah. No, you're right. You're right. There are actually. Look. This is able to collect data from this as well, Scorpio as well. So it's true. I didn't put here the. Tell me the name. Insight. Thank you. But yeah, because it was not meant to be a complete list. Yeah, we missed the part the for sure. Both ours are free and open source GPL. So Extra and Paraver are GPL. As far as I know, I think that Scorpi and Scalaska should be as well. Anyhow, one thing that I suggest you to is small here, but this project is something that if you are interested in these topics, POP is performance optimization and l'ultimo carácter, right? Yeah, let me open it. I have it here. POP. Performance optimization, productivity. Okay, so I suggest you to look into this because it's a European project that is not tied to one community, but is completely transversal to several community, and they work on big code like GROMAS, quantum expressions, this kind of huge code, and they do performance analysis at different levels. They do have their own methodology, and also their own tools. You see, if you go to tools here, you have a lot of them. Actually, this is more complete than what I was showing before. So I strongly suggest you to look into this project. And if you are really interested, I actually share the office. So I share the office with the compiler guy, and the office close to us is another colleague that is working here. So I'm pretty close to this activity as well. I can point to you to somebody that can explain more details. So I needed that for entering putting all together the RISC-V, the vector, and the performance tools. This is crude now because I removed a couple of stations of the train. Okay, so I'm not late anymore. Well, I'm late, but we still have 1 hour. 1 hour exactly. Okay, good. So now I want to jump into the European Processor Initiative, that is the project that is building a RISC-V core plus a vector unit. And that is actually, that has done already 2 tape outs. So we have a chip ready, up and running. And what I want to focus is the prototype that we use for software people, so for people that needs to run software in order to be able to work before having the hardware. Okay, that's the important point. Okay, a little bit of history. We started looking into ARM, as I mentioned before, long ago with this Mont Blanc project. And at some point, ARM was sold to SoftBank. And at some point, there was Fugaku #1 in the top 500. And at some point, we had this shift of interest also towards RISC-V. Okay, as I was mentioning before, there was a question about this at the beginning of the day. This has been technical, but also sociological, political, geopolitical, and so on. Okay, it's a little bit like turning a huge boat. Okay, so you're working on ARM, and at some point you're turning. It's, from the very technical point of view, is not much a difference. But if you look overall, yes, there is a difference. Okay. Anyhow, within API, we have 2 developments: a general purpose processor that is based on ARM, and what we call EPAC, API accelerator, that is based on RISC-V, green and blue. Okay, we are talking about the blue one. Okay, not about the RIA and the GPT, the ARM one. Okay, I'm talking about the blue one. If you are interested in the green one, we can talk about it, but offline. I don't want to, because we have a lot of things on the blue one. Here we have how the projects are built. I just skip the RIA one. Sorry, the ARM one is just the same core that you have on the Graviton 3. Okay, with the difference that here there is DDR and HBM at the same time. If you are familiar with this acronym, good. Otherwise, forget about this sentence. Okay, let's jump to the EPAC. So EPAC is a RISC-V accelerator. Okay, and here you have the picture. Unfortunately, I changed my bag. I always have one in my bag, but since I come from another place, I don't have my. But yeah, I mean, this is really a 2.5 centimeter by 2 is really a chip that has 3 kind of accelerator on it. Okay, so we were doing one chip with 3 different chip inside, if you want. Okay, because doing a chip is a lot of work, so it's a lot of money. So you want to save. You don't want to do 3 chips if you can do one in the same package. Okay, so there is the VEC, that is a scalar CPU plus the vector unit. There is STX and there is VRP. STX is for stencil computation for accelerating AI, and VRP is a variable precision unit that allow you to do floating point operation on different data size, increased precision also, up to 256 bits. Okay, what we are going to see now is the VEC. Okay, so not the other 2. back is where BSC is more important. Now, if I go into a block diagram, you have to imagine that chip like we have a core plus the VPU, several instances of them. Then we have the STX, we have the VRP. We have a NOC. NOC is a network on chip that connects everybody, so everybody can talk with everybody. And then we have the L2 caches, and then we don't have the memory, right? Because if you want a memory controller, you have either to build it or to buy it. So if you build it, you need a lot of time. If you buy it, you have a lot of money. Time and money are more or less the same. So what we did in this first prototype is a chip without a memory controller, but with a bridge, with a link to the external world, okay? So that the memory controller is outside, okay? So we can connect, for example, to an FPGA, and the memory controller, we use the memory controller into the FPGA. How many of you have never heard about FPGA? Good. Okay. FPGA stands for Field Programmable Gate Array. 4 letter, I got it for all of 4. Please acknowledge that. Good. So basically is a set of hardware like Lego bricks that you can configure. Is hardware, but you can configure the hardware to do the job that you need. Okay, so imagine it like a set of logic gates that you can configure. Okay, so if I need a memory controller, I can configure that as a memory controller and connect it to my chip externally and use it as a memory controller. Okay, if you don't need it anymore, you can reconfigure that. It's exactly like the Lego bricks. You can play a little bit with your car, unbuild it, and build a house, and that's it. Okay, so that's the same concept. For today, what I said is enough. For the recording, I know that is more complex than this, so I'm not sorry for the listener. Okay, but for today, it's just that. So the red box is what we have today into what we are able to map today into an FPGA. That's very nice because instead of waiting for a chip, let me find, I have to show you one slide now. The order now is completely skewed. I don't care. This one. Okay. The process of building hardware is long. Okay, I don't know if you are familiar with it, but you have to define the architecture on the blackboard. Then you have to do the RTL implementation. Okay, then you have to do the RTL verification because there are bugs, right? So you have to simulate that everything that you wanted to be there is there. And then you have to do the physical design because doing it at the blackboard, you have then to map it into the silicon, okay? And then when you have the physical design and everything is ready and bug-free, hopefully, you send it to the foundry. The foundry means global foundries. So you send it usually to Taiwan, and they usually take your description of your chip and they print it on a silicon. Okay, that process is also taking months. Then this silicon comes back, and you have to say stick it to something that has connection to the world, the small ball that you have underneath the chip. Okay, and all this process takes a lot of time. I would say that in the stage in which we are, the knowledge we do have, we take at least 1 year. Okay, if you are Apple, you have a lot of money, you know a lot of people, and maybe you are faster. Okay, but in the stage in which we are, is 1 year at least. So I have a room full of people. What do you do in that year? You have to, so full of people, software people, by the way. So you have to do something in that year, right? So what we try to do is to have prototypes that allow us to work in this window of time. Usually we have simulators, but that's not fast enough for working with big software, right? So For this, we use the software development vehicles. That is what I wanted to really explain now. So let me go back one moment to explain you which architecture do we have, and then I explain you the software development. Okay, I was here. Okay, conceptually speaking, since I feel a little bit of sentiment for the GPUs, so here is the block diagram, very high level of how a GPU system works, right? You have a host CPU with several cores with a host memory. Then you have a PCIe link. Maybe it's not a PCIe, maybe it's NVLink, whatever. You have some link that connects you to a device. Usually the device is your GPU, in which you have a lot of cores and also a separate memory, okay? Now, conceptually speaking, try to do this. Remove the device, remove the link, remove the device memory, take off the cores and put it close to the core, okay? And just moving boxes. So in the real life, it's slightly more complex, but conceptually speaking is this one, right? So I'm taking what I do in the GPU, the kernels that I'm doing to the GPU, and I bring it close to the core, okay? And the work that I'm doing in the GPU is what I'm going to do in with vector instructions. So that's a little bit the high-level idea. It's nicer, at least you have to acknowledge that it's nicer because you don't have two memory spaces, you have only one. It's also nicer because you can use one instruction set and not two, right? So when you program a GPU, you have the binary for the GPU and the binary for the host. And you can avoid the link that sometimes is a bug, okay? And now I go to the architecture of what we have. So the core is called Avispado, is a RISC-V core, is more complete of what I was presenting at the beginning. So it not only supports the 49 instruction, but way more than that. Is developed by Semidynamics. It is a company based in Barcelona. It is also partner in the project. And it has this tech spec, okay? So basically you don't need to understand all the blocks here. One important point is that is this box here, the gazillion. So here you have queues, so memory queues, integer queues, and vector floating point queues, okay? So here, basically, where are your instruction going? Okay, if you have a memory instruction, it goes for this queue, and this one of the feature of this core is that is able to shoot a lot of requests to the main memory. Okay, that's one very important point. The other important point is that has this OVI, open vector interface, that allows this core to be connected with a vector unit. Okay? And this is what we have basically. Well, the diagram of the vector unit now is not strictly speaking important, but you have to think that we are able to handle 256 double at the same time. Intel 8. In this architecture, 256. Okay, so imagine that when you do a vector load, you're going to the main memory and bring it 256 elements, not 8. 32 times more is a huge. So look at it in this table. I have one that is better. This. So this is Intel AVX. This is what we have. This is in scale, okay? So is a lot of data. If you are a visual person, please look into that, okay? So these are, one register is 16 kilobits, okay? As I said before, we have we need two things. One is that we need to request a lot of data to the main memory, and the other one is that we need a vector unit that is able to process all this. I have a question. This is the scalar and this is the vector I operate. So now my question is, do you imagine that when we load 8 elements in Intel, we operate all 8 at the same time, right? So when we load 256 elements, what do you think? Do we operate it all at the same time or not? Impossible, right? Physically impossible. Because we would need 256 functional units. That is a lot of silicon, too much. Okay, it costs too much. So what do? We do the same number of functional units at Intel, 8. Okay, but we process the vector 8 by 8. Okay, here I have a figure. So sorry if I continue jumping, but it's better to follow the. I have a picture. Right? So this is what we do in Intel. In Intel, we load 4 or 8 data and we operate it all at the same time. In a world in which we have a long vector, we have 8 functional units, in this case 4, and this is shifting, right? There is the guy pushing here the vector, okay? So if we have 256 double precision elements processed 8 by 8, how many cycles do we need? 256 divided by 8, 32 cycles, okay? So to process one vector instruction, we need 32 cycles if the data are already in the rest, okay? So it's really a lot of work, a lot of cycles, right? So that's important because I was already talking with some of you during the break. That's important. Why? Because we have scalar instructions that are taking 1 or 2 cycles. In the same binary, you have scalar instruction and vector instruction that are taking a lot of time, a lot of cycles, right? So now your single binary has different granularity of work, okay? That's very important. Is a little bit similar to what you do with the kernels in the GPUs, okay? At some point in your binary, you take a kernel and you offload it to the GPU because you know that you have a lot of work to do. So you send it to the GPU, you operate it on the GPU, and you come back. To do that, you have a lot of overhead. You have to send the data there, operate it there, bring it back, and so on, right? This way is a little bit similar, but staying in the same chip, right? Staying in the same instruction set, staying in the same memory space. Memory, yes, please. Yes, it's in the CPU world, it's called out of order, right? So if you have a CPU that is able to scheduling the instruction, changing the schedule of the instruction, you have some flexibility of being out of order. Yes. Yeah. The answer is yes, and is this one. So now you can understand better this, what I was saying here, right? Because if I operate 8 by 8, as long as I have the first 8 elements, I can start working. Exactly. Yes, please. I learned it from you. Yes. So for me, that word doesn't exist, but it's okay. So, Yes, yes.
Why I really want to understand why rather than
I think we are about to start a discussion that has some religious assumption behind it, and I'm tends to be inclusive, respecting all the religions, so I can explain how this works. We are all scientists, and you can understand how GPU works, but I cannot tell you what's better. Okay, because
one of the reasons
yes,
and you hope that but
yes. Here you solve the issue having a lot of requests going at the same time to them. And this I can show you a plot in which with one core, vector core, I can saturate the bandwidth to the memory. So if you take Stream, this afternoon you are going to run Stream. Okay, Stream is a benchmark that is doing operation on the memory, and you can, if you run it with OpenMP or MPI, you can on the x-axis adding cores, and on the y-axis you print the bandwidth, and you see that you need in an Intel machine, for example, you need several cores, more than 8, to saturate the full band. Right? With this one, with one core, I can saturate it. Same memory, same memory. Right? Because in the Intel system, you need several cores to send the request to the main memory to saturate the. So imagine that the channel that is going to the memory is like a tube, right? It's like a pipe that is bringing water to you, and if you ask for little water, you cannot fill that pipe. You need several cores asking for a lot of water, so you fill the pipe. No, yeah. In the case of the prototype, yes, but I have a system in which I can modulate the bandwidth and the latency. So I have a setup in which I can do the test that you want. Yes, in this case, I have a long latencies and a little memory, but I can move there. Yes. Okay. Going back to the original question, comparing to the GPU, one thing is the memory bandwidth that you mentioned. Another thing is that here you don't have to change. Sorry, you don't have to change your code. Your code remains portable. The worst thing you have to do is to add a pragma that can be disabled, and your code remains portable. If you have a CUDA code, you cannot port it. Well, yes, you port it to another CUDA system, right? But if I give you an application that is only for CUDA, you cannot run it here, or you cannot run it here at the same speed. You're telling me OpenACC allows you to have both work, right? Okay. Okay, that's if you can get from there the performance from the GPU, yes. But as I said, this is something that I can expect to be sort of unsolvable, and unsolvable in the sense that it's what I want to show you is just another way of seeing seeing the computation. So you are born in the era of where NVIDIA stocks are the most paid one in the stock market. Okay, so you are lucky that you have that devices. What I'm going to show you is just that it can be different, and it doesn't need to be what you are doing now. And I want just to tell you, don't contaminate too much your code, because tomorrow the stock option can change. That's the only, the stock market can change. Okay, that's the only message. Today we need GPUs, and we need good GPU programmers, and that's why the rest of the week is all centered to that, and that's okay. I don't want to fire here the war vector against GPU. I want to be scientist and say GPU works this way, vector unit works this way. I use GPU to give you examples, but not to shoot against. Yes, please. Yeah.
I that for reminding me of another similar context, the one in neuromorphism.
Yes.
So, is it possible to consider vector processor unit eventually the context of the neuromorphism?
Here, I have to admit that I don't have enough knowledge of neuromorphic so here ChatGPT wins against me, because I'm making. If anybody in the room knows about neuromorphic computing, I'm happy to engage the discussion. Otherwise, I acknowledge my ignorance, and I cannot answer really this question. Sorry. I should pay the $20 for you for the for this month, and you.
The same idea in the background. The sense that the user together, apart from the internal architecture of a chip, the robotic, you have also this kind of basic, and but I don't think for us thought about the fact that we can also do a sort of spectrum process.
Maybe one simple difference: can you boot a standard Linux on a neuromorphic computer? Yes. So this is one basic difference. Then we found it. For here, on this one, or say in the one we have here, we can boot a Linux operating system. Okay, a standard Linux operating system. I mean, really, where is that? With the graphical interface, you would be happy. That you are looking for. Good. Okay, so I go back to how do we program it. Basically, as a standard system, as a standard cluster, as you are familiar today. So you compile your code. We have the compiler that is able to generate vector instruction. You don't need to put in intrinsics in principle. We have compiler supporting auto-vectorization. You link your libraries. Of course, if we are nice, we have libraries that are already vectorized, right? So you are used, for example, maybe you use MKL, or maybe you use FFTW, or you use HDF5. I don't know which one familiar to you, but sometimes application depends to external libraries, right? So we can provide vectorized version of that. We don't have so many so far, but we have some of them. You write your Slurm scheduler. Sorry, Slurm job script. The scheduler is already there. It's the same Slurm that you use in your cluster. You submit the job, you wait for the result, and you analyze the output. With what? With the tools that I mentioned before. This is how to take advantage of the V extension. I go fast because this is we already seen. You can write assembler, up to you. You can write intrinsics, up to you. Or you can put pragmas, or you can leave it to the compiler, enabling auto-vectorization. Exactly. So strongly suggested the last 2 points, okay? stay happy, don't go up in this slide, okay? Then for what I told you before, we have this mess of 0, 7, and 1, 0, right? We have the two different version of RISC-V vector right now. So we also need two compilers. Right now we have these two compilers. The compiler for 071 is sort of stalled in the development. We are pushing the 10 because it's what actually will stay in the future. Sorry, and we have both intrinsics and auto-vectorization support, even if we promote the auto-vectorization. This already show you. And this is will bring us to the software development vehicle that I mentioned you before. So usually when you do a chip, you follow this path, okay? The green is the green is the hardware. Okay, you design the hardware, you do the RTL implementation, you do the post-design validation, and you repeat this loop. And then when you are okay, you send it to the foundry and you do the chip. Okay, for the pure software people that are trying to do software with these guys, they usually provide you just a model and a simulator and say, don't worry, the CPU will work like this, and they will give you software that is able to run a couple of hundred or thousand, or if you're like 1 million of instructions in some minutes or hours. Okay, so in a simulator, it's very slow to boot an operating system, for example. Okay? So what we suggest here is another way. We need the RTL implementation. We map that RTL implementation into an FPGA, and we boot a system, an operating system there, and we give it to the software people. Okay, that's the idea. And we can do performance analysis faster because on the FPGA we can run faster than a simulator. Okay, and that's the basic idea. And look, the important point are these two red arrows here. You see that there are no arrows from the software going back to the hardware in the classical world. Here we can provide feedback to the hardware people. Okay, so while we work on the software, I give you an example. Okay, they gave us an RTL. We put it into FPGA and we ran FMA. On the paper, the FMA should use 32 cycles. Why 32? Because 256 elements, 8 functional units, 256 divided by 8, 32. We run it and we count 35. What's going on there? 3 cycles. And you say, well, but it's not too much. It's only 3 cycles. But if every time you run an addition, you lose 3 cycles, it's a lot of cycles over a million addition that you have in your, okay? So these are the kind of inefficiencies. This was, for example, a stupid bug of implementation that we found at the beginning. It was nice because thanks to the analysis at the beginning, you can go back to the hardware guy and say, hey, but we would expect 32 cycles here and we see 35. They say, oh yeah, we fix it, is this thing. And the day after, you can generate a new bitstream for your FPGA and you have the system fixed. Okay. If you have to do this in silicon, you have to wait 1 year, and when the chip is back, it's bugged basically, and right. And these are the kind of things that in simulation are difficult to spot. Not impossible, but difficult. Okay. Good. Performance metrics. Let's go instruction mix. Here I have the AXP, the code that I showed you before. This is the vector implementation of the AXP. In orange, you have the instruction that are vector instruction. They start with V. The rest are scalar instructions. Okay. So if we want to measure how many vector instruction over the total, we call it vector instruction mix, right? Here I see 5 orange over 13 total instruction. Okay, so we have 38% in this small example, right? 38% of the instruction are vector instructions. And one can say, hey, 1/3 is vector, is very little, right? Then let's look into the cycles. Okay, to look into the cycles, you can look at the cycles spent in the vector unit divided by the total. This is cycles per vector instruction. Sorry, is this the one what I want? Cycles of vector instruction divided cycles of total cycles. Okay, so you can imagine that here you have your assembly, and here you have the time that is going from left to right. Okay, you have the scalar one that are white, and the vector one that are orange or yellowish, because the vset VLI is not really a vector instruction. Is a scalar instruction that takes very little time and do not activate work on the vectors. Is the one that I show you before to set the granted vector length. Okay, so that's basically, it's an instruction that is just, you are asking to the hardware which is the vector length, and the hardware is telling you the answer. So it's not taking really, it's not making real work. Okay, so percentage of clock cycle in which the VPU is active. So if we look at the actual execution, you see that the two loads, the FMA and the store, this is a store, not a load, sorry. This is a VSE. Okay. They're the one taking more time. Okay, so remember, we have 38% of the time, yes, 38% of the time of the instruction using 95% of the time. That's good, right? Because you have very little instruction that are instantiating a lot of work. Okay. Then we have average vector length. That's another good point. We were talking about this morning. So I have a vector of 256 elements. What about if I use it half of it or 1/3 of it, right? So ideally, we want always to use it with the maximum vector length. So let's look at these two examples. Okay, here I have two loops, two nested loops. This is going from 0 to 250, so it's looping 256 times, and the internal one is looping 6 times. If I leave it to the compiler is always trying to auto-vectorize the internal one, the internal loop, the most internal one. The compiler is usually not able to vectorize both of them. Okay? It only works on the internal one. What will happen with this kind of structure? That you will have 5 elements. So you will use 5 elements over the 256, right? So you're using the 2% of your vector. If we swap the loops, we are doing the same job, okay? But we can use the 100% the vector length. Okay? Sometimes there are changes in the code that are this kind of way that do not change the logic of the code, that allow the code to stay portable and the vector unit to work at maximum efficiency. Okay, this is just an example. I'm going fast because I want to arrive here. Okay, so we have one cluster of we call commercial scalar RISC-V platform. That is exactly what you're using this afternoon for your day. Okay, and then we have a cluster of FPGAs that we use as configured as one of these RISC-V core plus the VPU. Okay, so we have it all together connected. The red one are the scalar commercial. When I say scalar, I mean there is no VPU. Okay, and here the green, sorry, what's that? Gray. The gray are the FPGA. Okay, And everything is connected into the same network. So you can be this user, you connect, you have an NFS. So your home directory is shared between the Scalar and the, it's really like a cluster. Okay, you have a cluster of Scalar nodes and a cluster of vector nodes. On the Scalar nodes, we have an emulator. Okay, so if you have a binary, now question, if you have a binary with vector instruction and you run on a Scalar machine, what will happen? I compile and I say enable auto-vectorization. Then I run it on a Scalar CPU. Illegal instruction, exactly. You get an illegal instruction. Good. So that's illegal. That illegal instruction is a signal that is coming from the hardware to the system. Okay. If you leave it like that, the system will tell you illegal instruction and your execution died. But if you intercept that signal, you can take the status of your machine now, emulate in software what you want to do with that illegal instruction, and then continue your execution. Okay, so imagine you have your Scalar code. At some point, you have a vector instruction here. You get the illegal instruction signal. You trap all the information. You emulate in software what you want to do with your vector instruction, and you go back to the execution until the next vector instruction. Okay, that's, well, not really, well, it's smart, but it's terribly slow. That's true. Okay, but it allows to study the functional. So if a software is functionally working, okay. Yes, please. Statically during what? Yes. Because sorry, because we want the same binary to be able to run on the Scalar with the emulator, but also, sorry, I go on the actual hardware with the VPU. So we want one binary that is with vector instruction. We want to be able to study it on a Scalar platform or on a vector CPU. We don't want to touch the binary. Yeah, no, that's something we don't want. We want to have the same binary. So yes. Yes. But you know the man that is pointing at the moon and the rest of the looking at the finger of the moon, right? So you're looking at the finger, not at the moon. The point is that we don't want to have a perfect emulator. We want to study how the code runs on this system that has the VPU. For me, the emulator is just an accident. Actually, if I want to be completely honest with you, we have another kind of emulation that is based on QEMU that allows you to emulate the building blocks, and it's being way faster than this. So it's not a problem of having a fast emulation. The problem is that I want to understand how a vector code works with such large vectors. That's the point. Okay, so let's look at the moon, not at the finger. And for example, these are the kind of study I want to go to. Okay, let's jump. Yes, I have 15 minutes. I want to leave you 5 for the ideas of research ideas that I mentioned at the very beginning. Okay, so first we run assume that you have a complex code, not an AXP. millions of lines, okay, and you want to test it here. What do you do? Where, for which methodology do you use? Okay, so the idea that we propose is to follow 3 steps. First, you run in your commercial RISC-V platform, scalar only. You say, well, but Filippo, I mean, come on, you're selling us the vector, and you just do scalar only. It's useless. It's not completely useless because if your code is heavily GPU contaminated, you will not be able to run here. Okay? If your code is heavily Intel intrinsic contaminated, you cannot run in here. Okay, so you need a clean code that is able to run on a scalar CPU as a baseline. Okay, then we can activate the emulation and do the study that we can do the emulation, and then we can run on the FPGA. So which kind of study? Here we have computational fluid dynamics code that is called ALIA. Okay, here this is a trace, execution trace. Here you have time, here you have MPI processes, and you have different, this is real physics, it's not NAXP. So we are focusing on the element assembly kernel, that is the blue one, okay? And we are working on changing this vector size, that is basically the way in which the data are allocated inside the application. Don't confuse vector size with vector length, okay? Vector size is a bad name that the physicist decided to give to a define, okay? They call it vector size, but it could be Filippo that thing, okay? It's not the vector length. It's just a parameter that they use in their application to allocate the memory such that is more or less, say, contiguous and friendly for GPUs or vector. Okay. Good. So we take this mini app, so only the blue part because it was easier. We divide the mini app in phases. What are the phases? The loops, because we are interested in loops, right? So the typical scientific application are set of loops that are operating on different part of your data. And then we identified 8 phases, and we always only use auto-vectorization, no intrinsic, okay? Because we want that code to run on different machines. Okay, first we run on the scalar application. We change, we look at the different phases, and we look at the percentage of cycles, and we see that the phases 6, 3, 7, and 4 are the one more compute intensive. And we also see in this plot in which you have on the x-axis the different vector size. Let me move this. Okay. Basically, if I change vector size, the number of cycles doesn't change much. So you have a little bit of fluctuation, but basically, if you run scalar, you don't have much fluctuation here. But at least we were able to run scalar. So that means that we don't have dependencies with intrinsics. We don't have CUDA code interfering. Then we enable the auto-vectorization. And what do we see? We see the same plot, vector size on the x-axis and total cycles on the y-axis. We see that increasing the number of vector size is basically helping the compiler in getting vector instruction. It's good. Thank you. I stop the share. Okay. Thank you. Oh, thank you. Thank you for letting me. Okay, good. Resume share. Yeah, because I clicked there for moving this. Okay, sorry. Thank you. Okay, so if I enable the auto-vectorization, I already have some speed out. So in principle, one could say Filippo is 1, we can go for lunch, right? But no, we have the phases, and we can study per phases how well are these phases vectorized, okay? And so here we can see in a color code, we can see that phase 1 and 2 and 8 have 0% of vector instruction. So first I was talking with somebody of you that was saying, hey, but looking at the number of instruction is not really giving me a feedback of performance. It's true, but if I have 0 vector instruction, that means that that code is not vectorized. So maybe there is something bad there that prevent the compiler to vectorize that code. So we look especially into no, sorry. Let me go here. We run then on the FPGA, and here instead of looking at number of instructions, we look at percentage of vector cycles. The percentage of cycles in which I live, the vector unit is on. Okay, and here we can see that the phase 6 has some numbers that are growing. Let's check this column. Is AVL, average vector length. You see, is going exactly like the vector size. So the average vector length, that is the number of elements that I use inside my vector, is increasing with the with this vector size, with this parameter of the application. Okay, so that means that there is something is good, because when I increase the vector size, I'm filling my vector better and better, more and more, so I'm getting more and more performance. Okay? Let's focus on these 3 phases, because these are the 3 problematic phases. So next step, let's focus on phase 2, because it's costing more or less 30% of the time. And the problem in this case is that there was one of the safe assumption that I was mentioning this morning, right? So there was one parameter that was passed to a routine that was the compiler was assuming that could change, but in reality would never change. So we fixed that parameter that is called vector D, but it's completely irrelevant now. It's just that's part of the physics. It's not part of the computer science. Okay. So we fix that vector D in vector with the value of vector size that is mathematically speaking correct, and we have better vectorization. But sorry, we have auto vectorization, but we have worse performance. You see, the original one is the red bar, and the new one with the this constant change is going slower. That's counterintuitive, right? So we look into the vector length, and we see that the vector length that is using is not the maximum vector length, but is smaller. So we are not taking full advantage of the full vector. Why is that? And I go back to the example that I showed you before, because we have these 2 nested loops that are the most inner one is the one that is looping over a small number of elements. So we just swap 2 loops, and that's what we get, right? So vec2, so the optimization that we call vec2 plus VL is really decreasing. So now, so this is the original one, the red one. Sorry. The bar, the one with the bar like this is the one that we try to make it better, but in reality it gets worse, because we enable vectorization, but the vectorization is so bad that we are going slower than scalar in some cases. And then we swap the loops, and then yes, we take full advantage of the vectorization. Okay, these are the kind of study that we are doing on a real scientific code without having a chip. This is on a prototype that isn't an FPGA. So imagine that we are able to run computation fluid dynamics code now, 1 year before having the chip. When the chip is back, we already have not an XP, but we have real CFD up and running for that chip. Okay, this is really important if you think in the big picture. So you see that the idea of this morning was really to look into the microscopic details, but also zoom out and understand what's the impact of doing a new chip. Okay, and yeah, so these are after all the optimization. That's basically before the optimization. After the optimization, these are the results, and you see how the different phases. In this case, actually, it's just you have to look into the red one. That is the phase 2. Okay, is this one? No, I cannot go there. Is this one? Okay. You see here that it's getting solid, because when it's solid, I have it vectorized, and it's getting smaller and smaller. Okay, here I have a little bit of references, and now I jump this. This is a paper, short reason for long vectors. I leave it in the shared folder, so you can have a look. Yes, I'm finishing. What we are trying to do in that paper is studying the performance looking at 3 parameters. So latency to the memory, how much cycles I need to get a data, bandwidth to the memory, so how wide is the pipe that is connecting to the memory, and then the vector length. Okay, and the nice thing is that I want to show you just one plot. Probably this one. We use 4 different codes, and yes, this one. Let's see this. Okay. If I see the sparse matrix vector kernel, here I have different vector length on the x-axis, and the extra latency that I add to the memory. Okay, and I have a relative matrix that is printed here as a color map. Okay, a color code. And basically, when I add latency, of course, I go in the red zone, right? Because it's like having the memory far and far, and it's bad. If I am scalar, it's really bad. But if I am vector, if I have long vector, the added latency is not affecting me so much, because every time that I access to the memory, I pay the latency. But with vector instruction, I don't access too many times as when I'm scalar. Okay, so that's basically a little bit the idea of the paper. I leave it to it's really short, and we have just these 3 parameters, and you can see the stuff. Okay, and I go to the what I called beyond state of the art, because I want to finish with a little bit of ideas. So if you are in the performance optimization study and vectorization of application, there is multidisciplinary research that is in the style of the CFD code that I showed you, right? So you take an application, you compile it, you run it, and you start digging into what's limiting the vectorization. And that's the way to prepare the road to the vector CPU. And we have a lot of that codes. Then there is another layer that is vectorization of libraries. Okay, libraries like MKL are super well tuned, or for CUDA, probably you have the QBLAS and this kind of libraries, right? So we still don't have it for this kind of architecture. So we need one thing that we need people, we need hands, we need people with ideas, because sometimes you have to really reinvent algorithm in order to take advantage of this kind of architecture. Development of vector map library. For example, vectorization of NumPy, for example. NumPy is used by trillions of people, right? If you are able to vectorize it and have it up and running half decently on this architecture, you are basically giving a present to the whole humanity. Okay, then we have FPGA engineering. This is on another spectrum, right? So first it was software. This is more like FPGA engineering. So right now we are using one FPGA with one core and one VPU. If we are able to put two FPGA connected, one core and one VPU each, we can do a multi-core. Boom! So we can emulate even a multi-core system, right? So that's something that we don't have it. We still have to do it. Compiler development. The auto-vectorization is definitely not perfect. We have to improve it. We need the full support for Fortran. In the meantime, we have it, but not 100% working. And we can work on scheduling policy for long vector architectures, right? The thing that I was telling you before, we have small instructions that are scalar that are taking very little time, and then vector instructions that are taking long time. So how do we interplay that in order to be more efficient, right? Architectural study, effect of large vectors over caches, for example. This was mentioned this morning, right? So which is the effect if I have such a large vector? Probably I can implement something to bypass the cache in order not to contaminate the cache. Otherwise, every time that I have a vector instruction, I'm basically screwing my scalar code, right? Because my scalar core uses the caches to have the things there a little bit more at hand. And then I enter with my vector instruction and I wipe everything out. And my scalar core is saying, wow, okay, it misses for half an hour now, right? So these kind of things are interesting to study. DMA versus cache coherency, branch prediction, challenges in the out of order. Somebody was asking if we can do out of order. Yes, we can, but we have to understand how much it costs and how much silicon it costs. This, because basically what out of order means having the silicon smarter, but how much silicon it costs to have the silicon smarter, right? So how much money in the end? Complexity. The performance of the gather and scatter, we saw this morning that nobody expects them to be efficient as much as the units tried. The effect of the network on chip, and of course RTL implementation and verification, that is another point. And then the Linux kernel development, right? For example, support for vector in the kernels. Right now the kernel, I think, that runs Scala. Support for multi-threaded execution, the support of the study of the OS noise, the support for hardware counters is not in this slide, but hardware counters are really important if we want to measure something. And the performance tools that I mentioned at the beginning. And I think this is it. I finish at, we have 1 minute. We have 1 minute for your questions. We're losing the minute with the mic.
Have you measured the difference between your chip and GPU's power consumption?
Power consumption, not really, because it's a test chip and the technology are so different that does not make much sense. Because this is 22 nanometers. For those of you that understand this, so it's the size of the transistor that we have inside, basically. So these things is 22 nanometers, and probably a GPU now is what, 6, 4? Yeah. Okay, good. So it's really difficult to have it. We have a next iteration next year to do a chip that is 10, 7 nanometers, and no, 12 nanometers, and the multi-core, and it has all the memory controller on it. So that one makes more sense to measure and compare the power consumption. Okay, so I have to do this. We should do this with the serious faces, please. Ready? Are you there? Everybody's there? 1, 2, 3. Okay, now with the face that represent how happy are you of the morning, okay? Then I will look at the picture. So 1, 2, 3. Thank you. That's it.